Okay, for question 8, it is testing you on your concept about light, in particular, refractive index and Snell's law. So I have designed the question in such that part A, I'm trying to check whether you understand what is refractive index. So to check your understanding, I'm not going to ask you define refractive index. I want to see whether you know its meaning and its implication. So I come up with this question whereby the different components of light. So light normally, no matter what color, when it is in the air or in a vacuum, they will all travel at the same speed. So when you look at objects, whether it is blue, red, violet or what, they will all reach your eyes at the same time. But the funny thing about this is that when you let light passes through glass, it's different color, red, blue, yellow, green and all that, will actually slow down by a different amount. And as a result, you will have a rainbow. So down here, I'm trying to check your understanding on refractive index by telling you that, oh, the refractive index of red is going to be 1.51. And the refractive index of violet, it is 1.53. And I want you to show me the difference in the effect of different refractive index by sketching out its path of light of the different color. So there are a few ways to approach this. The most brutal way of doing is, that means you do it without elegance. You are given this value and you have no idea how to interpret this, but you know Snell's law. So the most hardcore way and not so elegant way is, well, dummy value. So what I will do is that, okay, I have no idea how the path of light of red and violet will look like in the glass bulb. But since you have given me the data, I will make use of the data. So this is the most brutal way. You come up with two cases. The first case is the red case where the n is 1.51, and then the other case is the violet, which is 1.53. You apply it to the same Snell's law. So you are talking about red light going from air to glass, and then the other case you are talking about violet light going from air to glass. So down here, if you look at the diagram, you do not know what is this, right? So if you do not know and you just want to know the difference in behavior, just give it a dummy value, maybe 30. Yeah, since sine 30 will give you some elegant number. If you don't want that, sine 40, sine 45, up to you. So what you can do is that you can sub in the number. Since you are doing the red light, this will be 1.51, and then the violet one will be your 1.53. Okay, you have to make sure that the dummy value here is being controlled, right? Then you just need to solve both sides. You will see that theta and the theta here will have different in number. So if this is 30 and this is 40, let's say, then what it means? Well, what it means is that you send the light in. If this is my red, this is 30 lah. So if I have 40 here, what it mean? Oh, well, it means my purple will be larger. Yeah, that's what it means, right? Yeah. So you can use this very brutal way of analysis. Just throw in value with a dummy value. You can solve this. Yeah. So this is the approach. If you have like clueless, you don't know what is going on, you have during your preparation you have not thought of that, but now the exam asks you to quickly approach it. So this is the surefire way that you can get a very definite answer. The more elegant way is that you approach it from the understanding of refractive index. So refractive index is basically a ratio between C, which is 3 times 10 to the power of 8, the speed of light in vacuum, over the V, which is the speed of light in that particular medium. In another word, you can rearrange the formula and make V the subject, which is the velocity of light in that particular medium that you are analyzing. And you will see that it is given by 1 over n times 3 times 10 to the power of 8. In another word, what this equation is telling you is that if your n is big, what happens is that the velocity, that means the speed of light in that medium, will be very, very slow. So the bigger it is, the slower it goes. So once you understand this, then the elegant way of doing it is, oh, okay, I know that red light is going to travel fast. in glass, and this guy over here is going to travel slower. So from this understanding, I need to go back to the drawing board. So I zoom in over here, I draw the exact same thing. So what I have is that I have the initial path of light, which is this. If the light doesn't slow down, it is going to follow its original path, right? So red light being faster, it will deviate a little bit. So what does this mean? This means that the slower, the light that gets slowed down more, it will bend further away. So this is the elegant way of doing it by understanding. Just by understanding that the violet light will slow down more, I would know that it will deviate more. So some of you at this point of time will be asking me, teacher, how do you know that when that light slow down is going to deviate more? Well, I hope you still remember something about wave front. So let's say this is the scenario, right? Light go in this direction, meaning that there will be wave front traveling like this, right? Correct or not? And when this happens, you will see that when light is incident into the other medium at a non-zero incident angle, you see that this part will enter the light first. If it enter the light first, that means this part here, when this part enter the glass first, so one part of the light will enter the glass first. So the bottom part will enter the glass first and it will slow down. But the other part of the light is still going at normal speed. So it is like you having a car, you have two wheels like that. This wheel is going at normal speed. And then the other wheel, this wheel, the bottom wheel, has slowed down. How will your vehicle turn? How will your vehicle move? It will start to turn, right? Correct or not? And the more this thing is going to slow down, the more deviation you will get. Correct? So as a result, if your violet light is going to slow down more, this light is going to bend more. Right? If your red light, the red wheel is going to slow down less, it will bend less. And if both wheels are not slowing down, then, well, it should theoretically go straight. Right? So you can work on that. And if you do not understand this very quick summary, please approach your teacher, okay, and understand this before your O-level. Okay, moving on to your part B. Part B is actually, I want to see how many of you are sharp enough to pick up that I am not asking for angle of refraction. I'm asking for angle of deflection. So many of you, when you look at the diagram, you immediately know that, oh, okay, I'm going to look for some angle and I'm going to use Snell's law. So very good. You have the glass side and you have the air side. So many of you did this very well. You substitute the air side, you substitute all this, and you find this. And then you thought that this is the correct answer. So that is why I want to check how many of you actually take a moment to actually ask yourself, what is this dita? From where to where? So I said many times, Snell's law, the dita is always from the normal to the ray. So if you look at this diagram, where is the normal? Well, this is the tangent to the curve. That means this is your normal. That means this is your dita. What does it mean by angle of deflection? Deflection means deviate from the original path. From original path. Where's the original path? Well, I can sketch it out, right? This is my original path. So, angle of deflection refer to the angle between the original path to your new path, right? This is your new path. So I'm looking for this angle. This is my answer. So how do I find this? Well, you need to use geometry. This angle here is 24. It means that this angle here is 24. So what is your answer? Your answer is going to be deta minus 24, right? So that is how I set my question to check how many of you take a pause and ask yourself, what am I finding? And how many of you can interpret a term on the spot